quick guide on taking a Node.js and Nginx application and deploying it on a Kubernetes cluster using Helm Charts. To quickly talk about the app that we'll be working on today, uh, it is a repository that has two Node.js applications, app and user service. App is a Node server that runs on port 3000. It has a couple of endpoints. One is a health check endpoint called /ping. There's another endpoint that is on the root, which returns a HTML page. And another endpoint that actually proxies to another service, which is on /API/users, which, if you can see here, hits localhost 4000 on a different endpoint and takes the data and returns it back to the client. And the server that runs on port 4000 is a user service. So the user service is again a Node.js application. It runs on port 4000. It has a single endpoint called /v1/users, which has a mocked set of users for this example, and returns those users back to whoever's consuming it, which in this case is app. And just to throw in another layer into the mix, there is an Nginx server that also has to run alongside these. Not in a local development environment, but say this is being deployed to maybe a production environment. We would want Nginx to sit in front of our localhost 3000 server to essentially allow accesses on port 80 and forward those along to port 3000. So that is a little bit easier for people to access our server. And just as a quick optimization, there is an error page that's rendered, which for any 5xx errors, it returns this maintenance.html page, which just says that the site is down for maintenance. So to see this app in action locally, we are exposing a start command through the package.json called start all, which internally runs the start app and the start user service scripts, which run the app and user service respectively. So now let's just jump back to the terminal and start both of the apps. And you can see that the user service is running on port 4000 and the server is running on port 3000. Now we can jump to the browser. We can hit localhost 3000. And we can see the root handler returning the static text that we were sending back from the handler. We can also hit the health check endpoint and we can see that that works as well. And we can hit API/users, which takes a call to localhost 3000, makes another network call to localhost 4000, which is the user service server, and returns the set of, and basically proxies the set of users from the user service back to the browser. And we can see that here, the user service was called and then the app server returned the /API/users call. Now that we have an application that runs locally, let's see what we need to do now to take it from here and make all of this run as we've seen right now in a Kubernetes cluster. So we don't have a production environment to test out all of our Kubernetes deployments, but we do have the means to set up one locally. So there are a couple of tools that need to be set up to first talk to Kubernetes and to also set up a local Kubernetes cluster. The tools are all available on the Kubernetes documentation page, but the two things that we'll probably need today are kubectl, which is a CLI tool that allows you to plug into a Kubernetes cluster to execute commands on the cluster. And the other one is Minikube, which allows you to spin up an entire Kubernetes cluster locally. And specifically for the demo today, we'll be using the Docker Desktop's Kubernetes capabilities. So another tool that will probably be needed today is to install the actual desktop version of Docker, not just the CLI. You should be able to verify if they've been installed correctly by running a version on all of them. So I have Minikube up, kubectl up, and Docker up as well. But before we go into deploying something to Kubernetes, the question still remains on how do we get something that is compatible with Kubernetes, right? And that's a prerequisite that we'll have to sort of address now, which is we need to run all of these applications that we have, which are the app server, the user service, as well as Nginx, in Docker environments, which essentially means that we have to create Docker images from them and use those images to run containers so that it's compatible in a Kubernetes environment. So to Dockerize our application, we need to start by creating a Docker file. And if you really think about it, we have three different applications here: our app server, our user service server, as well as Nginx, which all have to be Dockerized by creating Docker files for them, or creating Docker images using the Docker file configured for them. So let's first Dockerize app here. So we can create a file called Docker file under it, and most, if not all, Docker images start off with a base Docker image. So for example, here I need a Linux environment, and we also need Node to be running in that Linux environment. So here I'm just saying that use this version of Alpine Linux and also have this version of Node available, right? So that's the tag that I'm using here. Now our Docker image needs to essentially have three things, right? Or rather, the Docker file has to have three things. One is what code do we need to move from our host system into the Docker image? What port to expose? Because networking is sandboxed to the running container and your host system. So how do you interface between the two of them? Is by exposing ports. So which port to expose? And finally, what is the final execution that needs to run when the image is converted to a running container, right? So to move files from a host system to the Docker image, let's first create a working directory. So here, let's create user share app. So once you run the working directory command, you automatically create the directory and cd into it. So everything else that I do after this is going to be in with respect to that user share app directory. So the first thing we need to copy is our server code, which is going to be available in app/server.js, and we'll move it to our file called server.js inside this working directory. Now to make this server.js actually work, we need the node modules to be available so that all of our install packages are actually available on that image as well. So let's copy node modules as well. Now we know that the app server runs on port 3000, right? So we need a way to talk to this localhost 3000 server, and that can be done by exposing the 3000 port, which allows anyone who's using this image to be able to map a host port to the exposed port by the Docker image, thereby allowing us to directly talk to the server when it's running on port 3000. And the last thing is to have the final command that needs to run when you convert this image to a running container. So everything above this is at build time. So we build the image and keep it ready. But every time we spin up a container from that image, we actually execute what's been provided here in the CMD statement. Now CMD is just an array of strings. Each part of the array is going to be one space separated entity. So here we want to run the server, so we say node server.js, right? And this is pretty much all that we need to do to Dockerize our app server and have it running and exposing the 3000 port. So let's also tweak this and copy it over to the Nginx server and the user service server to Dockerize those servers as well. So now we have Docker files available for our app server, our Nginx server, as well as our user service. The only tweaks that were made were in user service. We copied over the user services node server and we exposed 4000 instead of 3000. And in the case of Nginx, we have a different base image. We copied the default conf to the necessary configuration route for Nginx, and we've also copied our maintenance HTML to another folder that's relevant to Nginx on that image. We've exposed port 80 because Nginx runs on port 80, and we are also saying that the Nginx should not run as a daemon. This is kind of important here because a container will stop running when the when this command ends, right? So if this reaches a conclusion, then then Docker thinks that your container has essentially stopped, right? Nginx, when you run Nginx, it runs as a daemon by default, which means that the command to start Nginx would start and stop almost immediately. So what we're just saying here is to turn off the daemon mode, so that the process that starts Nginx is also the process that's actually running Nginx as well. So now that we have Docker files available for all three of our applications, let's use the Docker file to generate Docker images for each of these applications and spin them up locally as containers just to see if we've Dockerized everything correctly. So to create a Docker image using a Docker file, you use the Docker build command. You can give it a context. So in this case, we're giving the current folder as a context. But the fact that we have three Docker files means that we can't let Docker know which of these Docker files are relevant for certain image build statements. So that can be done using a -f argument, which allows you to selectively say that this is the file I want to use. So in our case, let's say we want to run the build command for the app server first. So we can pass in app/docker file, and we can pass in the -t argument to now provide a name to this image. So the image is going to be called app server, and the tag for this image is v1, right? And tags is just a way for you to have multiple versions of the same image. So now we run this, we can see that a bunch of steps have run. Each of these steps are the steps that are available in our Docker file, for instance. And now when we run Docker images, we can see that the app server is available with the tag v1. Now let's quickly spin up this Docker image into a running Docker container to actually see if our app server is up and running correctly. So to run an image that has already been built, you can use the Docker run command. You can pass in the -d flag to ensure that you don't use the same terminal session for viewing the logs for that Docker image. So you basically detach it and let it run behind the scenes. Then you can pass in the -p flag to map a host port to the port that has been exposed by the Docker image. So for example, here I want my 3000 port to be mapped to the 3000 port exposed by the Docker image. And finally, we can pass in the image name, which in this case is app server, and the tag is v1, right? So the moment we run this, we get a SHA, and we can check the logs for this SHA by just running Docker logs on it, and we can see that the server is currently running on port 3000. So to test this out, let's jump back to the browser, and we already had this running, for instance, right here. So I can hit the health check endpoint, and we can see that the server is still running on port 3000, and this response is actually coming from the server running inside our Docker container, and not the server that's running on a local system, which we actually killed fairly early on. So cool. So the app server is running. So let's do the same exercise with the user service as well as the Docker, the Nginx service as well. So we can run the build command again, except now instead of passing the Docker file for app, we pass in the Docker file for user service. And the name for this is going to be user service. v1 is again the tag for it. We can see that this runs as well. It's been tagged. Now let's run the user service image, and we know that this wants to run on port 4000. And just to show that the host port and the exposed port don't necessarily have to be the same, let me run this on 5000 on my local system, but map it to the 4000 exposed by the Docker image. So we can see that this again has spit out a SHA, which means that the run command actually ran successfully. And we can see that it is running on port 4000. So when I jump back here, I can go to localhost 4000/v1/users, but this doesn't work because we mapped 5000 from our host system to the 4000 that's available on the image. So let's hit 5000 rather on our host system, and we can see that the response comes back with the mocked users. So user service is also working. So the last test is going to be for Nginx. So let's build the Nginx image and call it app Nginx v1. Mostly because Nginx is like an existing Docker Hub image name. So this runs as well. Docker run, and let's have this run on port 80. Let it map to 80 as well. And this is going to run app Nginx. Now let's see Docker logs for this. And we can see that everything's up and running. Now we really can't test proxy passes right now because none of these images know about each other. But one thing that we can test is if the maintenance page is rendered. So let me maintenance.html, and we can see that the maintenance page that we configured in our Nginx container, in our Nginx server is now being rendered because we directly hit maintenance.html. So as it stands now, we have 3 images, one for our app server, one for our user server, and our Nginx server, and all of these are up and running on our local system, and we've tested all of these and everything seems to be going absolutely fine. So now that we tested all of our Docker images by running containers locally and verifying that things are working fine, let's now move on to the Kubernetes side of things. So we did initially install a bunch of tools such as kubectl and Minikube to be able to run a local Kubernetes cluster, but we just did the installation. We didn't actually spin up the cluster. So we can run the Minikube start command to spin up this cluster. And as I mentioned earlier, we also want to use the Docker's Kubernetes capabilities and not run it on a different virtual machine within the system. So we can pass in the driver as Docker here. So once we hit the start command, a bunch of commands execute, and Minikube essentially spins up this cluster, which should take some time, maybe about a minute or so. Cool. Now that Minikube has spun up and there's a running cluster at this point in time, we can actually verify this by opening the Docker desktop again, and we can see that that Minikube is now controlling a cluster in Docker's context. So Minikube not just Minikube rather, but like Kubernetes installations usually come with a dashboard that lets you see what is running in your cluster and what are the different entities that are currently running and what the status of those entities are. So we can run Minikube dashboard, which tunnels and exposes the dashboard capabilities of the Kubernetes installation to your local system. So the moment we run Minikube dashboard, we can see that Kubernetes is running, and this is the default set of configuration for it. But we can also see that there's nothing else that's running apart from just Kubernetes as is. And that's where everything that we did before this, which is around creating Docker images, plays a part. So as part of the guide today, this is sort of what we want to recreate, right? We want to create a cluster that runs an Nginx server, which sits in front of 3 app servers, which again works on top of 2 user services, right? And the 3 and 2 are just just numbers that are being used for this demo, but technically this could be scaled up or scaled down based on whatever load that you see fit. And if you notice, in front of all of these 3 apps, we have services that are running, and what load balancer and cluster IP are is something that I'll get to in a bit. But we have the means of referring to a single entity who under the hood points to the individual running versions of the app. So for example, here all of these apps talk to a single service who then load balances between the 2 running user service instances, and Nginx talks to a single service which under the hood load balances between multiple apps. So this is the entire cluster that we are going to bring into our Kubernetes installation locally. And at this point in time, we have the images available for all of these, but how do we go about creating this cluster? And that's where something called resource manifests play a part. To talk about what these resource manifests are, we need to take a step back and talk about what pods are. So pods are the most atomic entity that can be deployed to a cluster. And what a pod essentially is a running instance of your application. Containers are also running instance of your application. So what's the difference, right? So a pod in most cases would be just the container that you're running, right? So the same container that we had for our app server, user service, and Nginx is just, for all intents and purposes, called a pod in the Kubernetes and world. But the definition truly means a running instance of your application, right? So if you have if you have multiple closely coupled containers, which have to really work with each other to function, right? Maybe you have like a Node.js server that's sitting on top of a database, for instance. In cases like this, you would want these containers to coexist at all times, and that's when a pod in this case could potentially have multiple containers under them. So again, the definition is a running instance of your app, whether it's one container, which is what is going to be in most cases, or multiple containers is on a case by case basis. So here, Nginx, each of these app instances and each of the user service instances are all pods, right? So here, if we want to create this cluster, we want one pod of Nginx, 3 pods of the app server, and 2 pods of user service. But then it gets a little bit manual to spin up pods one by one, right? Like we'll have to run the pod creation command 3 times to get the app server up and 2 times to get the user service up. And if you want to scale them in the future for maybe to support a much larger workload, we have to keep applying them over and over and over again. So that's where the first resource manifest that we'll be working with today comes into play, which is called a deployment. So a deployment is basically a declarative way to work on pods. So what I could essentially say here through a simple YAML file is that I want this pod to have this container, and I want these many instances of that pod available in my cluster, right? And I can also provide metadata to these pods to make other pods and services in my cluster understand these pods, right? And it's all done through a single YAML file. Now, the second type of resource that we'll probably be talking about today is these service type resources. So a service essentially sits in front of a number of pods and acts as a proxy mechanism between people who want to access these pods and the number of pods behind it. So I can scale up these pods to handle a larger workload, or scale it down, and I don't have to care about the individual IPs of these, but rather I would reference a single service, and that service would under the hood talk to these pods. So if let's say one of these pods gets removed for another pod, doesn't matter. The service still knows about the service is still the abstraction that everyone else talks to. Now, there are 2 types of services that this cluster has in this example. One's a load balancer service, and the other one's a cluster IP service, right? So the stark difference between the two is cluster IP services are only recognized by other pods and services running inside the cluster, whereas a load balancer service, as you can see here, is something that exposes an endpoint that the rest of the world can request to. So any requests that are outside the cluster can only come through a load balancer, not through a cluster IP, because this is only relevant within the cluster and not exposed to the external world. So in our example, we don't want our app server to be exposed directly. We don't want our user service to be exposed directly. We want all requests to come through Nginx. Maybe we have some like some authorization that runs here, or maybe we have some sort of pre-sanity or something of that sort, right? So we can do all of that here, and we can ensure that all of the requests are funneled through a single mechanism through this load balancer service. Now, I mentioned that all of these are resource manifests that control these different resources, and I did mention that all of these are YAML files, right? So let's just create a quick resource manifest that controls our app pods to begin with. So to actually see one of these resource manifests in action, let's jump back to our code base. So we want to create a deployment resource for app which specifies what container I want to run and how many instances of that container I want to run, right? So under app, I can create a file, let's call it deployment.yaml. And in this deployment.yaml, I'm going to specify my configuration for this deployment resource. So the first key is something that's pre-configured by Kubernetes. It's standard across all deployment resources, which is this API version. We are also going to say that the kind is deployment, which means that this YAML is going to be specifically to talk about a deployment resource. Now we can also provide some metadata, and like I said, these resource manifests allow you to provide metadata that for other resource manifests to like link to. So here I'm providing in metadata calling this deployment resource an app server deployment, right? And now comes in the main part, which is the specification for this deployment resource. So under the spec key, I can specify how many replicas I want of something, right? Now, what this something is based on a selector. So I can say that whatever is matching a set of labels whose name, or whose key is server and value is, let's call it app server, right? And what you provide under match labels is irrelevant. You can have any key and any value. It's just that you need to match this to something that you have specified in your container spec, which is what we'll be building next. So now we're just saying that whatever matches this label server, app server, spin up 3 replicas of that, right? So we can create a template for our deployment, and we can provide metadata to this. One such key is labels, and into the labels, I'm going to provide server, app server. So this is how this piece of the replica count is actually tying into the template for the pods. So now that we've provided metadata, we need to actually provide the spec for the pods. So the spec here is going to be the containers that we want to run as part of this this pod. So we can have an array called containers here. So the container name can be anything, doesn't really matter. It's just for like denoting, or rather this is the name that will show up in your Kubernetes dashboard. So we have the name. The image is what's important, which is what is the image for the container that we want to run, right? So in our case, we know that is app server v1, right? And since we want to run a local Kubernetes cluster, we don't want our images to be pulled from Docker Hub, which is what the default lookup for a Kubernetes cluster is. So since we have our images only available on local, I'm going to be putting an image pull policy for this as never, which means that never look it up, always use the images that are available. But based on your use case, you can, if you're using something that's already available on Docker Hub, you could omit this. Or if you're using something from a custom registry, again, you'll have to probably omit this. Then the next part is ports. So our container is going to expose ports. So we can provide a container port. So in this case, this is again an array of values, because a container can expose multiple ports. But in our case, it's just exposing a single port, which is port 3000, right? And here is where you can also provide other additional env variables. So just for the time being, let's just pass in env variables just to test this out. So we can pass in an array of env variables where you can provide a name for the env variable, let's say node env, and the value is going to be, let's say, production, right? So this is how a deployment resource manifest looks, where we just say that the kind is deployment. Here's some metadata about the deployment itself and the specification for it, where I say that for whatever spec matches this label, right, spin up 3 replicas of it. And I've also specified that this is what the label is going to be, which is server, app server, which is how these two tie in. And here's my spec, which defines what the containers are going to be inside this template, where I say that my container is going to be this image, and this is the port that I want to expose, and these are the env variables for my container, right? So now let's actually apply this deployment to a Kubernetes cluster and see if at least this part of my cluster is spun up correctly, right? So to apply certain resource manifests, you can use kubectl, which is again something that we installed early on. So the kubectl command here is now directly talking to the Kubernetes cluster that's running inside our Docker context. So kubectl takes a bunch of commands. Here we want to apply a new resource, so we use the apply command. We apply a file, which is what the -f stands for, and we want to apply the app/deployment.yaml, right? And this is going to take a while to run, and we can see that there is an error, and that's because DNS names need to have lowercase alphanumeric values. So let's change this to deployment. And let's run this again, and we can see that the deployment has been created. So now we can open up that dashboard that we had, right, using Minikube dashboard, and it will open this up, and we can see that there are 3 pods that spun up, and the container image is not present is the error that's showing up here, right? And that's interesting because we did build it locally, and we said that don't pull it from anywhere, right? So why can't it look further, or rather, why can't it find this image from a local system? And that's kind of where, and this wouldn't make sense, wouldn't be something that will show up in maybe a production environment, but at least for building it locally, there are some certain things that we need to do to get our Minikube talking to our local Docker environment. What I mean by that is, if I do Docker images, right, I can see that these images are available locally, but these images are actually not available inside Minikube, which is what's controlling the Kubernetes cluster there. So if let's say I run this command which uses the Minikube's Docker environment, and I run Docker images, I can see that my images are not available in the context of the Docker daemon running inside Minikube, and Minikube can only like pull up images that are within its Docker environment, right? So now we'll have to probably, now that we've run this eval command, we are now connecting our or rather using Minikube's Docker daemon on our host system, and now we need to rebuild these images on that Docker context to ensure that Minikube is able to see this. Again, this is not something that you would run into in a production environment, but for Minikube, this is a small little thing that we need to do. So let's run those Docker build commands again. So let's build app nginx v1. So it's going to like pull in everything and like start from scratch again. So if you can see here, it's spun everything up from scratch. And now if I run Docker images, I can see that app nginx is available. Now let's also create the images for user service. Which again happens from scratch. And let's also build it for our app server, right? Now when we run Docker images, we can see that our app server, our user service, as well as our app nginx are all available now inside Minikube. So let's jump back here, and you can either use the dashboard to like check things, or you can also use the kubectl command to see what is running right now. So here, for example, I've gotten the pods, for instance, that are running inside my cluster. And now I can see that the pods are running, right? And that's because we now have the image available inside Kubernetes. And because Kubernetes is a self-healing environment, which means that if anything errors out, it tries to bring it up like over and over again until it succeeds. So in the previous case, we didn't have the image available, so it failed. But the moment we made the image available, it tried to restart it and found the image, and now it's running successfully, right? So let's also maybe check the logs for one of these running pods. So I can do a kubectl logs and the pod name, and we can see that the server is running on port 3000. But again, these pods are running within the cluster, which means that there's no way for us to access these pods directly from the outside world, right? So, but then we can see that there are exactly 3 replicas running for this service. So now, like I said, if you have a larger workload and we want to scale things up, we can come back to this deployment.yaml, and we can probably change the replicas to 4, and come back to a terminal and apply the deployment again. and we can see that deployment ran. And now when we get pods, we can see that there are 4 pods now running, where the latest pod has spun up only recently, which is around 4 seconds ago. So that's how we can declaratively scale up and scale down running instances of our application through a single resource manifest, instead of having to spin them up one by one, right? So now that we have a deployment running, let's add a service to abstract away the deployment or the pods behind the deployment from other services that are running in the cluster. So our service is also another type of resource manifest that you can add. So if you jump back here to the cluster, you can see that we want our apps to sit behind a cluster IP service. So we can come back to the code base, create a service.yaml file. And this is going to be similar to how we defined the deployment manifest. So there's an API version. However, the API version here is v1 for services. The kind is going to be a service. So it was a deployment for a deployment manifest, and for service manifest, it's kind service. Similar to a deployment manifest, we can provide metadata to the service manifest itself. So we can have metadata. Name is app server cluster IP service, and yep, there we go. And all of these resource YAML files have a spec that defines what the manifest is supposed to do. So the spec for a service is going to define what a type is. So you can have either a load balancer type or a cluster IP type. Since we want a cluster IP, so we'll add the type as cluster IP. And every cluster IP service has requests that come into it and requests that go from it, right? And that's what the port's key defines. So you can highlight which port you are going to expose to the external world. So in this case, my port is going to be 80, but requests that come in on port 80 need to be funneled to the actual pods, and each pod is running on a certain port, right? So in our case, the pods that were defined by this deployment YAML are all running on port 3000. So we can have our target port set to 3000. So what this means is requests come to the service on port 80, but then get sent to whatever sitting behind the service on port 3000. And now we need this service to work on the pods defined by this deployment, right? And that's again where the metadata that we define here in terms of the selector comes into play. So if you see here, we had a label called server app server. So we will use that here, which means that I want this service to sit in front of pods that are controlled or have the label server app server. So now let's apply this manifest as well. So apply -f app and service.yaml, and we can see that the service has been created. Now when you do a kubectl get, you can now get services, which is the resource type that we've introduced into the system. So if we get a service, we can see that there is an app server cluster IP service that is running on this cluster IP, but exposes no external IPs, which means that again, it's an IP that people or pods within the cluster can reference, but no one from outside the cluster can make calls to it. And we can also see that this is exposing the AT port as a TCP connection. And if we go back to the Kubernetes dashboard, we can also see that we have the app server cluster IP service, and we can also see that like if we click on this, we can see that this cluster IP service is sitting in front of these app server deployments, which are the pods. So they are able to talk to each other because we've provided them or provided the service the right selector to select. So now if it doesn't matter how many pods this scales up to or scales down to, this cluster IP service is still going to be the abstraction that everyone talks to. They don't have to talk to the pods directly. So now that we have our deployment that's orchestrating our app server pods, and we have a service that's sitting in front of the app server, let's go ahead and construct the rest of this cluster. So we need a cluster IP for user service and a deployment that has 2 replicas for the user service pod. And we have a deployment for Nginx with 1 replica and a load balancer service that sits in front of it. So there's some amount of copy paste that's going to happen here. So let's take this deployment YAML and put it inside the user service as well. And we can change the deployment name from this to user service deployment. We want 2 replicas behind it. The server is going to be called user service, and the image is user service v1. And we know that the user service exposes port 4000, not 3000. So let's change that out as well. Now we also need a service for this user service. So let's add that here as well. And we change this to user service cluster IP service. It's again a cluster IP type, port 80, target port is 4000. And we want this to talk to any server that matches, or any label whose key is server and values user service, which should match this key here. So let's apply the deployment and service for the user service as well. So kubectl apply -f user service deployment YAML. So we can see that the deployment has been created. Let's also go ahead and add the service YAML. So we can see that that's been created as well. So if we do a kubectl get pods now, we can now see that there are 4 instances of app server here, but then now there are 2 instances of user service that have also been spun up and they're running as well. So this is being controlled by the user service deployment YAML that we added. And let's also do a kubectl get services. And we can see that there is a user service cluster IP service, which is also running on a certain cluster IP. And to see if it's connected correctly, we can go to the Minikube dashboard, or rather the Kubernetes dashboard through Minikube. And we can see that the user service cluster IP service is here. We can click on it and we can see that it's sitting in front of both the pods defined by our deployment. Now let's do the same for Nginx and see if this whole thing works end to end, right? So let's copy this deployment and add it to our Nginx folder. It's going to be called the app, or let's just call it the Nginx deployment. We want 1 replica of this. The server is going to be called Nginx. The server label is Nginx as well. The name of the container is Nginx. The image is actually app Nginx, since we had namespaced it. Again, v1. And container port exposed is 80, and there are no environment variables for it, so we can exclude that. Now let's put another service in front of it, and this is where things may change a little bit. So we'll call this the Nginx load balancer service, and the type here is load balancer now, right? And it's going to receive requests on port 80, and the target port is the same as the exposed port by the Nginx container, which is port 80. And the selector here is going to be Nginx, right? Which should match our server Nginx thing here. So now that we have this, let's spin this up as well. So we can do a kubectl apply -f of Nginx deployment. So now Nginx is spun up, and we can do a kubectl apply -f of the Nginx service.yaml, right? So let's do a kubectl get pods just to see if the deployment went through. And we can see that one Nginx pod is up and running, which is about 14 seconds ago. And we can also see that we can also get the services. And we can see that there is a Nginx load balancer service, which has a cluster IP. And if you notice here, instead of having none as the external IP, we have a key here called pending. And this in a production environment would actually resolve to an IP that you can hit. But since we have a local Kubernetes cluster, we need to do some mapping through Minikube to get this to work. But just note here that the external IP is something that Nginx load balancer service will potentially expose, that we can now consume from our host system directly, which we couldn't do with the other cluster IP services, for instance. To get this Nginx load balancer service expose an external IP, we can use the Minikube service and the service name. So what this will do is it will try to tunnel this IP to the host system so that we can access it directly. So we can hit this in, we can see that, yep, so we are somehow able to consume the internal IP here, right? But if you notice, the moment we go there, it says that the site is down for maintenance, even though we're hitting the slash endpoint, right? That means that we are actually getting a 5xx back from Nginx. And to kind of highlight why that's happening, it's because if we go to our Nginx default conf, we've actually said that it has to proxy pass to localhost 3000. But now that we've moved to a cluster type environment here, where each of these pods the pods now have their own IPs, right? Localhost 3000 doesn't make sense anymore. This Nginx needs to hit this cluster IP service, and these apps need to hit this cluster IP service, and so on. Now, if we come to the Kubernetes dashboard, which let's boot it up quickly again. We can see that each cluster IP is exposing. We can see that each cluster IP service is exposing an IP that we can consume. So technically, our Nginx pod needs to hit this app server IP here, or rather, the proxy pass has to hit this, and then every call that we make from our node server, by the way, which is here as well, where we hit localhost 4000, also has to hit this specific IP. But here's the thing. Something that we configure here in our local Kubernetes deployment may not hold true when we go to another Kubernetes environment, right? Let's say we have a production environment that we need to, like, we're testing here and we need to take this to a production environment that someone else is offering. We cannot be guaranteed that these cluster IPs are going to be the same, right? And Kubernetes does solve this through service name discovery, right? Essentially, what you can do is you can go in to any place that you want to reference another another pod or another service, and you can reference them by name. What that means is, if you want Nginx to hit our app server cluster IP service, instead of giving it an IP, we can rather just give it the cluster the service name itself. So I can now tell Nginx to proxy pass it to app server cluster IP service. And now this name gets resolved by the cluster whenever calls are made to this like the DNS resolution does happen within the cluster for this domain name. So let's add this here, and similarly we'll have to make one change in our app server to also consume the user service cluster IP service instead of localhost 4000, right? But now there is one concern here, which is that if I now run this locally, this is going to start failing because this doesn't resolve to anything, right? So here we can probably put a small check saying that my response can either come from localhost or from a cluster IP service based on my NodeEnv, which we've powered through the deployment resource manifest. So we can say that if the NodeEnv is production, then my response will be from this cluster IP service. Else, my response is going to be from localhost 4000. So this should ensure that we don't break a local development environment for this. So now that we have this, we are also powering the NodeEnv, by the way, from here in the deployment YAML. So we can pass in our environment variables here. Now let's rebuild the images and use the new images in our deployments so that the end-to-end cluster starts working as expected. Okay, so let's first rebuild our app server, which is what we've changed, and let's make it v2 now. Similarly, let's rebuild Nginx. App Nginx v2, and we don't necessarily have to rebuild our user service because that hasn't changed, right? And now that we have new images, let's go back to our deployment YAML. In our app deployment YAML, we just need to change our image to v2, and let's go to our Nginx deployment YAML and change this to v2 as well. Let's just verify once that both of these app Nginx and app server are available as v2. And now let's apply the app deployment first. So we can see that that went through. So now we can see that a bunch of our app servers are now terminating and new ones are running, and we can also see that they were spun up quite recently. And over the course of time, we can see that the complete handover from V1 to V2 has happened. So we are back to only 4 running containers, and the ones that were terminating are now completely terminated. And now to confirm that we are now running V2 in this environment, we can go back to Minikube, the Minikube dashboard. And if we open up any deployment, we can see that we have our app server deployment that is now pointing to the images app server v2, right? Which means that we have configured a new version of the app to go out. And something that's crucial here is if we go back to the age of every pod, we can see that none of the other pods have changed. It's strictly only the app deployment that has gone through, which means that only the app server code has spun up new versions of the code on the cluster. Now let's also do that for Nginx. So let's kubectl apply -f the Nginx deployment YAML, because there's a new version of the Nginx image as well. And we can see that the deployment got configured. You can get the pods, and we can see that the Nginx pod, the old one is terminating, and the new one is now spinning up. And give it enough time, and the pod has now, like, it was terminating at this point, and now it's completely been removed from the cluster. Now let's open up Minikube and tunnel the Nginx load balancer service. And now instead of the 5xx page, we now get the page that's rendered directly from our app server. So the proxy pass from Nginx to the node server is working correctly. We can also use the health check endpoint to get the response back from the app server. And now to truly check if it works end to end, let's hit the API/users endpoint, which, by the way, just to reiterate, calls the user service cluster IP service and returns the users from there. So now hitting /API/users, we can now see the data for the users now being passed from user service to the node server, to the app server, and from the app server through Nginx and back to us. So now we've essentially constructed this entire cluster with all of these services now running in front of these deployments. And anytime there's any code change that we need to do, we can just go to a deployment.yaml file, change the tag version or change the replica count, and reapply the deployment to have a new version of or the new look of our cluster up and running as we see fit. So while the resource manifest files provide a very declarative way for us to control our pods and our services in our cluster, we can already see that it's getting a little bit out of hand with the number of deployment files that we're maintaining and the number of service files that we're maintaining. And this is for a simple application that has two services and an Nginx layer on top of it. Now, if our cluster gets slightly more complex with more services coming into play, we have a lot of these YAML files that we have to start paying attention to and orchestrating the right way. Not to mention that we have only talked about 2 resource manifests here. Technically, there are a lot more resources that you can apply to your cluster, such as auto-scaling configurations and like config maps and dynamic configs and so on. So there is a significant overhead here. Not to mention that there's another problem, which is the fact that if you see the environment variables that we're passing in and the replica count that we're passing in, all of these are sort of set in stone for a certain type of environment. For instance, here, I could say that this deployment YAML here for my app server gives me a good idea of how my production cluster is going to be. But let's say I have a staging environment that needs a different env passed to it and a different replica count, right? Because maybe the staging cluster has a little less resources to use. So maybe I want like 1 replica for this server on a staging environment, and I also want to pass in my node env as staging here. the easiest way would be to have two duplicates of this deployment YAML, one for production, so I can have deployment-production.yaml and deployment-staging.yaml, but then that's just two environments, right? What if I have more permutations and combinations of the different values I provide here? That's steadily going to linearly increase with each type of variant of my application that I'm going to have. So all of these are potential problems that you could run into when you have Kubernetes running your applications at scale. And so to solve this problem, we have something called Helm, which sits as an abstraction on top of the resource manifest that we have as part of our Kubernetes infrastructure. And what Helm allows you to do is it allows you to think simply in terms of the blueprint for your cluster. So you define what resources need to be part of your cluster and also what values need to be passed to these resources, and all you have to do is think in terms of this blueprint and generate something called a Helm chart. Applying a Helm chart to a Kubernetes instance will spin up the entire cluster for you, and similarly, uninstalling a Helm chart would also remove the entire cluster in a single go. And you can upgrade this chart with any smaller changes that you have to make over time. So Helm is available to install directly from a script, which is available on the Helm documentation site. So once you have Helm, you should be able to check if it's up and installed using Helm version. So here we can see that it's running version 3.4.0. But what is this whole Helm chart concept, right? So what a Helm chart is again a simple YAML file that defines what your chart name is, what your version of your chart is, and what does the chart work upon. So to kind of highlight how all of this works, let's create a file called k8s, and let's create a chart.yaml file inside it, right? So this chart.yaml file is going to have a name. So let's call this our app cluster, and it's also going to have a version. So let's call this version 1.0.0, right? Now this chart is everything that we need to tell Helm that there is something that I want to install to a Kubernetes environment, and the name of the chart is going to be called app cluster, and this is the version for it. Now, what does this chart work upon? Like I said, it takes care of all of the resources for you. All it just needs to know is what are the resources that you want to put into your environment. And the way that it knows that is using this templates folder. So if all we have to do is move in all of these deployments and services that we have in separate folders into this templates directory. And now Helm will be able to understand that yes, these are the different or the various resources that I want to install and deploy to my cluster. So let's move in our app deployment and app service, and let's just call it something different. So it doesn't have to be called the same thing. So I can call it app deployment and app service. App service. I can also move in my Nginx deployment and my Nginx service. So let's rename this as well, Nginx deployment and my Nginx service. And let's also move in my user service deployment and my user service service. So I can call this my user service and my user service deployment. So now that we've moved all of this here, we've essentially co-located all of the different resources that we need to install in our cluster, and all of these will now be orchestrated by Helm, which I'll show you in a bit. But another key thing that I want to touch upon is the values.yaml, which is another key component to a Helm chart. So what this values.yaml file allows you to do is provide a YAML file of any format. There's not a fixed format here, but you can provide keys and values in this YAML file, and you can use those keys and values inside your various templates, which should potentially solve a problem about having different environment variables and different configurations for our different environments, right? So let's take the app deployment as an example here. So let's say I want to configure the replicas, and I also want to configure the node env here, right? To start simple. So let's just close a couple of files and simply concentrate on the app deployment and our values.yaml. So I can create a namespace called app server in my values.yaml, and I can say that the name of my app server is going to be called app server, right? Just a simple key called name whose value is app server. And I also want to provide some details about my image. I want to, my image name is going to be called app server. My image tag is v2, right? And let's also say that my exposed port is 3000, right? And the replicas that I want to have for this by default is 4, but based on the environment I can change it. So I have this map created in my values.yaml. So now let's see how we can use this to parameterize our app deployment to make it seamless for us to integrate this in different environments. So the syntax that's used here is based on the Golang templating language. So let's plug in a couple of these values. Let's replace the replicas for now. So I don't want 4 to be baked into my app deployment, but rather controlled through my values.yaml file. So I can say values.appserver.replicas is what is going to be the value for this replicas key. So I have app server and replicas, right? And similarly, let's just change up some stuff here. So I can also interpolate the values. It doesn't always have to be a single value. So for example, here my image is going to be dot values dot app server image dot name, right? And this is colon for the tag, and values dot app server dot image dot tag, right? So we have essentially interpolated two values into a single string, which is joined by this this colon here. And we also have the configuration for the exposed port. So let's use that here. So I have dot values dot app server dot image dot exposed port, right? And another thing that we wanted to do was we wanted to have different environment variables for different environments that we wanted to deploy to. The default is production. So let's also have a key called env and node.env and use that here. So dot values dot app server dot env dot node.env, right? And another thing that we can probably use is this name key to kind of replace all of these app server instances, so that we can we can be sure that we always have a single source of truth rather than having it split across multiple places. So let's just select that and change all of these instances to dot values dot app server dot name. And again, this is just a way for us to ensure that some consistency, so that we don't make mistakes where maybe potentially we've introduced a typo here in the match labels and suddenly my deployment is not annotated correctly. So now we have this app deployment that has essentially been templatized, and all of the values are now flowing in through our values.yaml. Let's also do the same thing for our app server, right? So we can add a key called service. Doesn't have to be called service. It can be called anything. There's no fixed format. And this is kind of where you'll start to see the benefit of having it templatized and having a single source of truth. So we have this app server. Let's just change this to also take our values.appserver.name, right? And it's a cluster IP service. So let's also just add that here. So type is cluster IP, and let's use that here. Values.appserver service.type. So tomorrow, if we want to swap it out for a load balancer, we can just come here and change this one value. And here is where we can start seeing the benefit of having a single source of truth. So we have this exposed port, right? And we're using that to define what our container port is going to be. But we also need to ensure that our app server, or rather our cluster IP service, is also talking to the same target port. So to maintain the same value, we can just point to the same values.appserver.image.exposed port. And now we can be certain that since there's a single source of truth again, changing this one value will ensure that the deployment will see the right container port, and the app service will also forward the request from port 80 to the exposed port correctly. And let's also change this selector, app server.name. And there we have it. So now we've essentially templatized both our service as well as our deployment, and the values for it are coming through our values.yaml. So let's just take a quick minute to templatize the rest of our deployments and services, and then let's see how all of this plays well together when we do a Helm install. So now let's just see what we've done so far. So we have our app server, which has some values. We have Nginx, where we say that this is our image name, image tag, exposed port. We have one replica, and the service type is load balancer. And user service has a name. The image is user service, tag is v1, expose is 4000, and two replicas. And we've used those parameters. So we've used all the user service values in our user service deployment. We've used the same user service values in the service as well. And similarly with Nginx, we've used all the Nginx values in the Nginx deployment as well as in the Nginx server. So now that we have this chart YAML and the values YAML, we can now use the Helm command to use this chart and deploy it to our running Kubernetes instance here in the Docker context. Right. So first things first, let's first purge all of the pods that we have running so that we can see how Helm helps you set up everything from scratch. So you can use the kubectl, delete pods, or rather let's delete the deployments first rather than the pods. So now we should see that all of the pods are terminating, and let's also clear up all the services. And we can see that all the services have been destroyed. And now if we get pods, they're all in the state of terminating still. And if we get all the services have also been purged. So let's just wait till all the pods are done. Cool. So now we can see that there are no more pods, which means that we have a completely empty cluster, no services, no pods. And we can confirm this by using the dashboard again. Minikube dashboard. We can jump in here and we can see that there are no deployments, no pods, and no services. This is the default service, but no custom services that we've configured available right now in our cluster. So which means that we have a completely clean installation. So now we can use Helm to install this entire chart, which is what we've created here under the k8s folder. The chart configuration is available in chart.yaml. The values.yaml contains all the values to work upon the templates that we have for our various resources. So we can come back here to Helm install, and what Helm install asks you is for a path to the chart folder. And let's just see this run as a dry run before we do the actual installation. And let's also ask it to generate a default name for us. So if we notice here, we can see that all of our resource files are just being console logged to us because we ran it as a dry run. But what's very, very neat here is that all of our template values have been replaced. So if you see here, we can see that the Nginx name has been replaced everywhere. The Nginx image name has been replaced correctly. Replicas, the same thing with our user service deployment. So we have a single values.yaml that's now driving all of these templates, which means that we can technically use our values YAML to drive different values for different environments. But before we get there, let's not run it as a dry run now, and let's do an entire installation of the chart folder, and let's generate a name. and we can see that the deployment has gone through successfully. And let's just open Minikube, or rather open the Kubernetes dashboard in Minikube. And in a single installation command, we can see that 3 deployments have been pushed to our cluster. All these deployments are running all of these pods. We can see 1, 2, 3, 4 instances of the app server, 1 instance of the Nginx deployment, and 2 instances or 2 replicas of the user service. We can also see that our services are up and running. We have our app server cluster IP service, our user service cluster IP service, and the Nginx load balancer. This is still waiting because we have to do the tunneling through Minikube, but in a production environment, this would have resolved to an external IP. And now, just to check if this is working correctly, let's fire up the tunnel to our load balancer service, and we can see that everything's running as expected. We can go to /API/users, and we can see that the data is being funneled end to end now through the cluster. Now, Helm is great in the sense that if we do a Helm list, we can see the various running Helm installations that are deployed to our cluster. We can also see that this is the chart name and the chart version, and it's good practice to maintain a proper semver for the chart version. So charts can be reused by other charts. So similar to how Docker images have base images, right? You can have a base chart version also. So if you want to share this chart with another team or to the public, you can have your chart name and a version associated with it and actually like share this, and other folks can use this as a dependency for their chart, which means that you'll bring all of your resource templates and the values YAML, and they can then extend upon that to build their use cases. So it's a good practice to follow good semver, which means that anytime there's a change to the chart itself, right, not the values YAML, that's slightly debatable, but when you have changes to the resource templates or any new resource templates get added, it's good to update this version. So let's make a small change to see how a second deployment can happen to the same cluster. So let's go back to our code base, pull out our user service, and let's say we want to add another user to a list, right? So whose name is Jordan Doe, right? So at this point in time, we need to recreate another Docker image which contains the new code, and then use that Docker image in our values YAML to configure the new value for our deployment. So we can come back here, we can do a Docker build, and we can build our user service again, except this time let's tag it as v2 because we have a new version of the code. So we've tagged this as v2. Let's also check if the image is available, and we can see that user service v2 is available now. Now let's jump back to our values.yaml. So if you go to k8 values.yaml, we can see that user service image tag is v2. Let's bump that up to is v1. Let's bump that up to v2, and let's do a Helm upgrade. Of the same installation, and let's provide the path to the chart. So now what Helm is doing is essentially taking the chart that we have, the new version of the chart, and applying it on the same installation that we had earlier, but with the new values of YAML, and that's why we have a new revision of the deployment. So now if we do a kubectl get pods, what's interesting here is the old user service deployments are now being terminated and new ones have taken their place. If you see here, these are just a couple of seconds ago, but none of the other pods have been touched in any form, right? Which means that you can use the same chart to deploy a version of your cluster, but there is a clean diff that's done to ensure that running pods that have had no change in the new version of the chart are not touched and are running as they were before. So let's ensure all the terminating pods are gone, and they have. And to actually see if the code is up and running with the new user that we've added, let's again tunnel to the load balancer service through Minikube service. And let's hit /API/users, and we can see that the new user is now available as part of the data array, which means that the new Docker image has spun up new containers in the cluster, and those containers are now serving the new code. So this is how you can use Helm to, for all intents and purposes, just envision how your cluster is going to look along with the various values that you want to use for this version of your blueprint, and use these values in templatized resource manifest files. And the beauty of this is, if since these are templatized, you could potentially override these values or YAML values through CLI arguments if you want to deploy to a different environment. So these are all default values that we're applying to our templates. But if you have a separate environment, let's say like a staging environment, you can use the Helm install CLI to pass in a different value for app server env, node env, for instance, or app server replicas, for instance, based on the environment that you want to deploy to. So that allows these templates to be far more generic, and we don't have to have copies for every environment that we want to deploy to. So similar to how we have Helm installed to spin up an entire cluster, and Helm upgrade to upgrade the values in a cluster, we can use the Helm uninstall command to completely purge a cluster as well. So instead of having to go and delete all of our pods and all of our deployments and so on, we can just use our chart, which is anyway like a blueprint of what we've deployed, as a stencil to also keep note of what needs to be removed when you want to remove a installation. So I can just do a Helm uninstall and the name of the Helm installation, and it'll tell us that the release has been uninstalled. And now if we do a kubectl get pods, we can see that all of the pods that are controlled by this chart are being terminated. We can see the deployments have been purged, and we can also see that the services have been purged as well, apart from the default one. But the ones such as the user service, cluster IP service, app server cluster IP service, as well as the load balancer service have all been purged as well. So in a single command, we can get an entire cluster up and running. In a single command, we can have a new version of a cluster installed, and with the single command, we can have the entire cluster purged as well. So this is, in a nutshell, how we can get a Node.js and an Nginx application up on a Kubernetes cluster using Helm. I hope you guys found this useful, and I'll see you in the next one.